Okay, this is 2.1 part B. This is actually a fairly short lesson. This one's all about the special triangles. And the special triangles are a memorization thing. We get exact values for some of these special cases. But anyway, let's just start off. There's a relationship between the sides and angles in every right angle triangle. This is what we learned last year. This is our SOHCAHTOA. SOHCAHTOA. Every single right angle triangle has these relationships. All of these angles are already kind of memorized and they're all stored in your calculator. So if you say what sine of something is, it'll just tell you what that ratio has to be. So sine of any given angle is equal to opposite over hypotenuse. Cos is adjacent over hypotenuse. And the tan is opposite over adjacent. So we're all pretty good with that. That was an easy part in grade 10 math, and we're all pretty comfortable with that. Special right angle triangles. There are three angles that have exact measurements, which we should be able to memorize, and which actually come up a lot in regular calculations. Right angle triangles come up all the time because you can turn most triangles into a right angle triangle by adding an altitude, and these angles come up all the time as well, especially when it's items that are being built by humans. So if you're in construction or something like that, often you're going to get 45-degree angles, obviously, are going to be directly across, and 30 and 60 are very common as well. So these special triangles are not rare cases. They actually happen a lot. So examples of them. Well, the 45 triangle is actually an isosceles triangle, but usually we draw it on its side. So there's a right angle triangle where this length is equal to that length. That's our isosceles triangle, and this is going to be our 45-45-90 triangle is what we call it. So this is our one really common case, and the other one are the two end ones are actually paired together. So in the other one, and actually if you want to find it, you can actually draw an equilateral triangle. This is one of the ways to get it. So if you have an equilateral triangle, and they often use the side lengths of 2 for a reason that we'll get into later, and then they draw an altitude line that comes down, then half of this triangle is actually going to be, this angle right here is still the same as the equilateral triangle, so that's our 60 degrees. And this angle up here was cut in half, so that's just 30 degrees. So that's our 30, 60, 90, we call it. So 45, 45, 90, and 30, 60, 90 are our two special triangles. And they have usual measurements as well. The measurements we don't care about as much. It's not the specific measurements that we care about, is what I should say. It's the ratio between the sides. So for this triangle over here, we actually usually call this side length 1, call this side length 1, and then if you do the Pythagorean theorem, this side up here will end up becoming root of 2. It becomes 1 squared plus 1 squared, which is 2 square rooted. So it should be root 2 up there. So these are our usual ratios. They could be much bigger. You know, this side length could be 5, in which case this over here would be 5 root 2, because it's 5 times bigger. But the ratios hold the same. In this triangle, we call it the 1, 2, root 3 triangle. It's called the 1, 2, root 3, which is a nice way of saying it, but it is a little bit confusing because you need to think which is the longest side length. And at first look, it kind of seems like it should be this one, but root 3 isn't actually the longest. Let me get my calculator. Root 3 is 1.7 roughly. So the longest length is actually the 2. The 2 becomes the hypotenuse. You're going to have to memorize that as well. The shortest length is the 1. So the 30 degrees is the smallest angle, so it should produce the smallest length. The 1 is across from the 30, and the root 3 is actually over there across from the 60. So those are our two special triangles, and we'll see some more details about them. So 45, 45, 90, 1, 1, root 2, and 30, 60, 90, 1, 2, root 3. Okay, let's draw them out in nice good details. So we make sure we have them memorized. This is a 90-degree angle. This is a 90-degree angle. This is 45 degrees, 45 degrees. Always look for the pointy one, that's what I do. So the pointy has to be the 30 degrees, and the bigger one is the 60 degrees. And then we draw in our side lengths. So this is 1, 1, root 2. And I've seen some people add a variable there as well. Sometimes they say it's 1 times h, so they might call this like h root 2, which just shows that it could be amplified by a certain amount. This is just the general ratio that we're talking about. And in this one, it's 1, 2, root 3. 2 is the longest side, root 3 is the middle, and 1 is the short. So those are our two special triangles. And now let's talk about the different trig ratios that exist in them. So for this one, we're going to do sine of 45, we're going to do cos of 45, and we're going to do tan of 45. So sine of 45, and it doesn't actually matter which 45-degree angle you pick, because there's two ones, so it'll end up being the same ratio. Sine is opposite over hypotenuse, or opposite over hypotenuse. Either way, it's 1 over root 2. So that's how you get it. Now, unfortunately, there's a problem right away. We never like to see radicals in the denominator. This is the right answer, but for rules of simplicity, we always want to rearrange this. Just as if you gave me a polynomial, and the polynomial said x minus x squared plus 4. You know, that could be the right answer for a polynomial, but we don't write it that way. We always rearrange it to make it look biggest to smallest term, so it would be negative x squared plus x plus 4. And that lets our future math become much easier. If you're used to seeing things in a certain way, it makes things much quicker when you're going to rearrange them in the future and trying to analyze them in the future. So we never leave radicals in the bottom, so we actually have to rationalize this denominator. I'm not sure if you've talked about that before. To rationalize the denominator, it means we need to turn this denominator into a non-radical into a rational number. What we do is we actually have to multiply it by root 2. If we multiply it by root 2 times root 2 will make positive 2. But in order to do that, you can't multiply by some weird number because that'll change the expression. But you can multiply by 1, and that will not change the expression. So you multiply this whole thing by root 2 over root 2. So the actual answer to sine of 45 is root 2 over just 2. So the roots cancel down here. It's root 2 squared, which becomes just positive 2, and a root 2 stays on top. This is what we want to write every single time. Cos of 45, this is going to be nice. So a over h. So that's also 1 over root 2. So that's also root 2 over 2. Exact same answer. Sine of 45 and cos of 45 are the same thing. Tan of 45, so TOA, O over A, is just 1. Nothing you have to do for that one. That one's nice and easy for us. It's 1 over 1, which is 1. Okay, into this triangle. Sine of 30, cos of 30, tan of 30, and we also need sine of 60, cos of 60, and tan of 60. We've got two different sets this time. If I'm going too fast, just pause the video and make sure you get all this copied down. So sine of 30 is of 30, it's O over H is a half. That's nice and easy. Cos of 30, so A over H, adjacent means touching, so which one's touching the 30 degrees? A over H, root 3 over 2. Tan of 30, T O A, 1 over root 3, which is equal to, we need to rationalize the denominator. We don't actually write it the long way. So multiply it by root 3 over root 3. So it's actually root 3 over positive 3 is what we get. Always rationalize the denominator. So you'll probably get to this one first, but you always have to turn it into this one. For 60, now this is actually going to get a little bit quicker. So sine of 60 is O over H. O over H, that's actually the same thing. Sine of 60 is the same as cos of 30. That's the same ratio, so it's root 3 over 2. Same thing with cos of 60. Cos is adjacent over hypotenuse, which is the same as sine of 30, which is 1/2. And tan of 60, O over A, well, this one's just root 3 over 1, which is just root 3. Make sure I did that right. Opposite over adjacent, yeah. So those are our trig ratios. Everything on this page, with the exception of this stuff, you have to have memorized. And actually, we're going to go further than this. We're going to build all this into the unit circle. I'm going to save that till I'm done the lesson with the grade 12s, and then I'm going to go over that with you guys. And we'll do that at the end of the lesson. Copy and complete this table without using calculator. So calculators can only give you decimals, and as we saw, all those ones with roots in the expression, they would give you decimals that go on forever. So that's why we're calling these the exact values. So every time we say I want an exact value, you need to think your special triangles. Because if you use your calculator, you're going to get, well, let me show you what root 3 is. Root of 3, 1.732050808 ... It goes on forever. It's one of our irrational numbers. So that one's not good for getting to Mars, is my common expression. It's no matter what, you've rounded with that number. But if you give me the answer root 3, that's the exact right number, and you can do things with it in the future. Like if you ever multiply it by another root 3, you get the answer 3. Whereas the decimal won't do that. So in here, I want you to try and do, you should pause the video now, try and go from memory, see if you can write down what all these special trig ratios are. Okay, I'm going to do them. 45, these ones are root 2 over 2. Root 2 over 2. And 10 is 1/2, was it? It's hard for me to do without writing out the triangles. Just 1. 10 was 1. Sine of 30, so that was opposite over hypotenuse. That was 1/2, which is the same as cos of 60. Well, is also 1/2. And then the other one that we had was root 3 over 3. That was our complicated one that we had to rationalize. Root 3 over 3. And then tan of, I gotta look these ones up again. Tan of 30 is root 3 over 3. Oh, root 3 over 2, sorry. Root 3 over 2. Root 3 over 2. Tan of 30 is root 3 over 3. Yeah. And tan of 60 was just root 3. Or root 3 over 1. Good. Example 2. Find an exact distance. Allie is learning to play the piano. Her teacher uses a metronome to help her keep time. The pendulum arm of the metronome is 10 centimeters long. For one particular tempo, the setting results in the arm moving back and forth from a starting position of 60 degrees to 120 degrees. What's the horizontal distance the arm moves in one beat? Give an exact answer. So we got to use our special triangles. Don't use your calculator. First thing, let's draw a picture. So we have our metronome, and it goes from 60 degrees. And this is our standard measurement angle. So it means 60 degrees from the x-axis. So it goes from up here. Maybe we'll draw on that. So that's 60 degrees. And it goes all the way to 120 degrees, which is going to be over here. 120 degrees. So it does something like that, and we care about the horizontal distance traveled between these 2 points. So how far is that? A couple ways you could do this one. Basically, there's 2 different triangles you could see. We're only going to care about right angle triangles because that's what our special triangles are. So we're only going to deal with half of this at a time. So you could treat it as this triangle up here, or you could translate it to the triangle that's downwards using our reference angle, which might be a bit easier. So I'm going to actually draw this in down. Now I'm going to talk about this triangle right here. So the thing we care about is this x value right here. We want to find this horizontal distance, and this should be the same thing over here. So whatever our x is, we just have to times it by 2 to get our horizontal distance. We know the length of the arm is 10. Now at first glance you'd probably want to put it here, but the length of the arm would actually stick up a bit because as it goes, it's going to go in a circle. So this length here isn't actually 10. This length here is going to be less than 10. The length of the arm, our radius, is 10. So our hypotenuse in this case is 10. Our x is the same as this x down here. And this is a 60-degree triangle. So why don't we draw it out one more time? Basically, we have this triangle that we're dealing with. It's a 60-degree triangle with a length of 10, and we're looking for the horizontal distance in it. Okay, so what do we know? We want adjacent and hypotenuse, so that should be ka. So cos of 60 is equal to adjacent over hypotenuse. So we know the angle. If we can use this one in the calculator. Putting this in the calculator is asking the calculator what the ratio is, but the calculator will round for you. But we know the exact values now, and we know that it has to equal this ratio. So instead of using the calculator at this point, we're going to replace our trig question with what we know. So we know cos of 60 is a half. And then it's just a proportion. One ratio has to equal another ratio. We know that this should be 1 compared to this is 2. If this is 10, what does this number have to be? Well, it should be 5. And to solve the proportion, you move the 10 up. So x is equal to 10 over 2. So x is equal to 5, which makes the horizontal distance 10. So therefore, the horizontal distance is 10, do we have a units? 10 centimeters long that way. It's also 10 centimeters long that way. Is 10 centimeters long, I should say. Good. You should try the U-try on your own first. So pause the video, see if you can do it on your own. Okay, drawing the diagram, 45 to 135. So it's 45 degrees up to 135, that's 45 degrees here as well, which means these two halves are equal, which makes sense because it's a metronome. So once again, we're going to have this little triangle where this is the thing we're looking for, and it's the same 10 centimeters here. So we can say exact same measurement, cos of 45 is equal to x over 10. Okay. Now if you're thinking cos of 45, you want to have that number memorized, or you can draw out the triangle really, really quick. You just say, hey, that's a 1, 1 root 2. So cos is, if I call that my 45, adjacent 1 over root 2, or root 2 over 2. So root 2 over 2 is equal to x over 10. So now we're replacing it with the exact value for cos of 45, not the decimal your calculator would give you. Solving this one, so the 10 comes up and multiplies. So x is equal to 10 root 2 over 2. Do not turn this into a decimal. If you turn this into a decimal, you've wasted everything that we're trying to do. If you're going to put it in a decimal, you might as well just use the cos of 45. We don't want it a decimal. We need to leave our roots as roots. So the number that we're multiplying just stays in the front. This is a whole number. We like it. The root is just at the back like a variable, is the way you want to think of it. Sometimes you can do things to make this thing interact. You could pull numbers out of it, or you could put numbers inside of it, or if you ever happen to multiply by another root 2, you can get rid of it. But until those times, you leave the other number at the front. So all we want to do here is actually do 10 divided by 2. This is all one term, so all you have to do is divide any part of that term. You don't do it twice. You do not divide 10 by 2 and root 2 by 2. You divide every term once. So let me just make that clear. If it was 10 plus root 2 all over 2, that would simplify to 10 over 2 plus root 2 over 2. That is how you would do that one. But for this one, it's just 10 divided by 2. So the answer is 5 root 2. That's our x, but that's not actually our total distance. So we actually have to double this. So therefore, the horizontal distance is 10 root 2. And we leave it just like that. That's our exact answer. Exact answers are a big deal. So if I ask for an exact answer, write in the question, does this one say that word? What's the exact? Pay really close attention to that. You're going to get docked at least a full mark if you don't give it to me as an exact answer. If you give to me, what is root of 2 times 10? If you give to me 14.14, you're going to get at least a full mark off this question, because this was about if you could recognize the special triangle and solve it with special triangles. So make sure you can do that. Okay, you can try these questions when I'm done with the grade 12s. We'll go over the unit circle together.